Gravity is everywhere. It gives shape to the things you see around you, holds you to the Earth, and keeps the planets and satellites in orbit. Considered to be one of the most complex and mystifying forces of nature, gravity has been a source of debate and numerous conspiracy theories for years, ever since it was first discovered. Now a team of researchers has come out with some new studies that claim to have uncovered the real source of gravity, and which could fundamentally change everything we thought we knew about the world around us and how it actually functions. Welcome to Factnominal, and in today's video, we'll be taking a closer look at what could potentially be the answer to one of the world's most mysterious forces, gravity. You've heard this story before. A young Isaac Newton sitting under an apple tree gets hit on the head by a falling apple, and this sparks a eureka moment for the young man, which, as we all know, prompted him to ask perhaps one of the most important questions ever to be asked. Why did the apple fall straight to the ground rather than go sideways or upwards? Although there's much debate to this day if there was an apple that really did fall on his head, the point is he noticed something, and that something would prove to be one of the most important observations in physics. Several ancient Greek and Indian philosophers had also observed that objects naturally move towards the ground, but it took a flash of insight from Newton to bring this truth to light. The average person probably wouldn't think twice seeing a fruit fall from its tree. But Sir Newton, being the curious, complex character that he was, found this rather odd. And thankfully he did, because it's this very simple yet fundamental question that led him to lay down the fundamental law of gravity. And that was just the beginning. But what exactly is gravity? The textbook definition of gravity reads, "The force that attracts a body towards the center of the Earth or towards any other physical body having mass." But gravity is so much more complex, and it truly is not easy to contain it within a single definition. We can understand gravity in our daily lives as the fundamental force that dominates each and every moment of our life, probably without us even taking a moment to realize it. Whether that's giving our muscles something to struggle against, the pressure we feel when we climb up a hill or slope, or simply the heavy force that pulls us right back down to the ground when we jump in the air. In terms of space, gravity is very important. We know it as the force that actually holds all the planets and celestial bodies in orbit around the Sun, merges different galaxies together, or simply collapses hydrogen clouds into stars. According to Newton, he outlined his law of gravity in 1687 in his book Philosophiae Naturalis Principia Mathematica, or simply translated to Mathematical Principles of Natural Philosophy. German physicist Johannes Kepler, almost a century prior, had already developed 3 laws governing the motion of the 5 then-known planets: the law of orbits, the law of equal areas, and the law of periods. However, the problem here was that he didn't have any theoretical model for the principles that were governing this movement, and relied more on trial and error for the course of his studies. But Newton was able to take the laws of motion he developed and applied them to planetary motion in order to develop a very rigorous mathematical framework for this planetary motion. In his book, he came to the conclusion that the apple and the moon were both being influenced by the same force. He named this force gravitation, from the Latin word gravitas, meaning weight or heaviness. He officially defined the law of universal gravitation as every particle attracts other particles in the universe with a force that's directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Newton compared the acceleration of the moon to the acceleration of the apple or other objects on the Earth. Through his calculations and models, he was able to lay down the 3 most fundamental laws, which today we know as Newton's laws of motion. First, an object will not change its motion unless a force acts on it. The second law states that the force of an object is equal to its mass times its acceleration. And lastly, the third law states that when two objects interact, they apply certain force to each other in equal magnitude and in the opposite direction. Newton's law of universal gravitation goes beyond the objects and things that we see on Earth and extends gravity into space. More than anything, people often attribute the fact that Newton didn't necessarily discover gravity, but rather he discovered the important fact that gravity is universal and all objects are attracted to each other with a force of gravitational attraction. Newton's law of universal gravitation is a widely accepted theory, so much so that it's taken as a fact, not just a theory. But with the passage of time, it would soon become clear that his description of things may be fraying at the edges. Although Newton was able to establish that gravity is universal, he wasn't quite able to get some important questions answered. There was yet a lot to learn about gravity, and more importantly, how exactly does it work? Then, in 1915, Albert Einstein rose to the challenge. He came up with a theory that completely changes science's perception of gravity. Expanding on his theory of special relativity, which he'd published 10 years prior, Einstein argued that space and time are inextricably connected. However, the theory hadn't quite taken into consideration the existence of gravity. In the special relativity theory, he determined that the laws of physics are the same for all the non-accelerating observers, and that the speed of light within a vacuum is the same, regardless of the speed at which an observer travels. He concluded that space and time were interwoven into a single continuum known as spacetime, and that while events may occur at the same time for one observer, they could occur at a completely different time for another. After much study, he found through his equations for the general relativity theory that massive objects seemed to cause a distortion in spacetime. So, in Newton's gravity, only an object's motion through space is affected by the gravitational force, whereas according to Einstein's general relativity, both space and time are distorted by the presence of mass. Newton's theory was extremely simple, but couldn't quite explain Mercury's peculiar orbit around the Sun, where the planet's orbit shifted much faster than Newton predicted. There had to be something missing, and this is where Einstein's theory was able to offer a different view in order to make sense of what exactly was going on with the first planet in our solar system and the closest to the Sun. He reasoned that each object curves the fabric of space and time around the forming of a sort of well that other objects, or even beams of light, could fall into. Take a simple example of the Sun as a bowling ball placed on a mattress. With its mass, it created a depression that then drew the planets closer to itself. His theory went on to be confirmed by more than a century of experimentation, and specifically the 1919 solar eclipse, in which the path of light from the distant stars actually got shifted by the Sun's intense gravitation, and it shifted exactly by the amount Einstein had predicted. The question arises then, did Einstein prove Newton and his theory of gravity wrong? Not at all. Newton's work was rather descriptive and used a simple mathematical equation for what was observed, whereas the issues surrounding his theory were the very reason Einstein was able to dig deeper in support of his own theory. As of today, Einstein's theory of general relativity is arguably the most successful theory of all time. The predictions of general relativity have never once failed. But that doesn't mean there hasn't been some concern and debate over the past few decades, as with any theory out there. But if there is one thing that perhaps Albert Einstein couldn't explain, is black holes. Well, at least not entirely. All the predictions of his theory are usually the result of a very simplified version of his equations, but soon it was realized that some aging stars would not be able to resist the pull of gravity and would collapse in on themselves and form what we know of as a black hole. A team of scientists believe that the massive celestial structures might just be the exception that the theory of general relativity may not be able to explain. There, in the inky depths of the black hole, the laws of the universe seem to fold in on themselves, and these models of gravity may not hold very true. First, Einstein sought to debunk some of the things put forth by Newton, and now scientists may be on to something new. According to the study that was published in the journal Science, it shows that gravity works just as Einstein had predicted, even right to the very edge of the black hole. In this case, we take Sagittarius A star, a supermassive black hole that's sitting right at the center of our Milky Way galaxy. Study co-author Jessica Liu, astrophysicist at University of California, Berkeley, states that we now have the technological capacity to test gravitational theories in ways that we've never been able to do before. Einstein's theory of gravity is definitely in our crosshairs. Co-leader of the new research, Andrea Ghez, stated that while Newton may have had a great time with his description of gravity, at some point it became clear that it had many gray areas, and Einstein offered a more complete version of what gravity is and how it works. She states that with the advance in technology and new testing capabilities, it's quite possible that we may very well be close to finding something a little more comprehensive that would allow us to describe and truly understand gravity in the context of black holes. While Isaac Newton had a rather simplified view of gravity and was able to put forth the basics, there was still that gap where it wasn't quite sure of things like Mercury's orbit. Afterwards, Einstein came in and made sense of what exactly was happening with Mercury. But now, Ghez and her team wanted to truly subject Einstein's theory to a much more rigorous test. They observed what happened when light from the star S2 passed Sagittarius A star, which just so happens to be 4 million times more massive than our Sun. They used a trio of giant telescopes in Hawaii in order to watch the bluish star make its closest approach to Sagittarius A star in its 16-year orbit around the gigantic black hole. So, if Einstein was right, the black hole should warp space and time in a way that would extend the wavelength of the light from S2. The waves would stretch out as the intense gravity coming from the black hole drained their energy, thus causing the star's light to shine from blue to red. In the experiment, there were 3 possible outcomes. Either it proved Einstein right and turned red the way it should, or second, it could continue to flow blue and would actually give credence to Newton's model of gravity, which actually doesn't account for the curvature of space and time, or it could turn a completely different color and leave us all with a completely new model of gravity altogether. But as the experiment went on, what do you know? It turned red. So Einstein's theory still continued to hold true. What did the team have to say about this letdown? Ghez had a rather optimistic view when she stated that it didn't matter, but that the simple fact that the team was able to look in a place that hadn't been done before and explore a regime that hadn't been explored before was a big step forward in itself. Despite the team not finding anything conclusive to debunk Einstein's theory or prove that it has any flaws for now, scientists know that at some point of time within the black hole, Einstein's theory of relativity will stop working. Nobel Prize-winning physicist Kip Thorne said, "The curvature of space-time is so extreme that Einstein's general relativity fails. We yet don't understand how it works when the thing that you're dealing with is extreme." The team is rather looking forward to what they have to achieve within the next decade. The experiment no doubt pushed the envelope and brought them one step closer to perhaps discovering a whole new aspect to gravity, which we perhaps have been overlooking this entire time, or simply haven't been able to study yet. The research team plans to use a new generation of high-powered instruments that would allow them to conduct many more tests of gravity around black holes. They'll continue to keep a watchful eye over S2 to see if its orbit precessed as Einstein would have predicted or expected it to do. And if it doesn't, then voila, they'll have found the next big thing in physics. The team states that within the next 10 years or so, they're looking to push the theory of gravity to its limits in every way and on every object possible to hopefully start to see some cracks. On the other hand, new ARC-supported research has confirmed that Einstein's theory of gravity accurately describes current observations of black holes right from the smallest to the largest. By observing the shadows of supermassive black holes residing in the centers of galaxies and gravitational waves, which are the ripples in the fabric of our universe from colliding stellar mass black holes, the general relativity theory can be tested to its extreme. Scientists from the ARC Center of Excellence for Gravitational Wave Discovery, the Event Horizon Telescope, and the LIGO Scientific Collaboration have come together to outline a consistent approach to exploring any deviations from the general relativity theory, and have found no evidence for deviations so far. The EHT generated images of the black hole at the center of the galaxy M87 that's several billion times the mass of our Sun. The LIGO and Virgo gravitational wave observatories have been using gravitational waves from the merging of stellar mass black holes. The combination of these measurements was used to test theory, and sure enough, there weren't any deviations to be found. So, what does all this mean for us? Well, frankly, not much. If we jump, we're still probably going to get pulled back to Earth and land on our feet due to gravity. But what a discovery like that could potentially mean is we could get much closer to understanding how our universe was born and how we got to where we are today. Not to mention, it would help to understand and track gravitational waves far better. Whether or not the team succeeds in their endeavors to uncover more about gravity, its origins, and how it affects black holes, only time will tell. One thing is for certain, gravity is undoubtedly one of the strongest and most complex forces of nature. And the more we try to learn about gravity and uncover its secrets, the weirder it gets. That's all for today, folks. So, what do you think? Do you have any theories about gravity? Let us know in the comments. And please don't forget to smash that like button and subscribe to our channel so you don't miss another video. Thanks for watching, and we'll see you next time.